So you can once check if you can share the your PPT,
Share
then
the screen. Okay, let me.
yeah.
1 second. I will share. Yeah. And PPT is visible, right? The
Yeah,
screen?
it is visible.
Okay.
We'll wait for 2 more minutes and then.
We can.
Good evening, Hirawat sir.
Good evening, sir.
Satyendra. Hi Anand.
Hi,
How are you?
Satyendra.
Hello,
I'm
Satyendra.
fine.
So I'm seeing Anand after a long time, long time. After I'm tech.
Yes, yes. I'm also good to hear you after a long time.
Yeah, thank
How
you.
are you?
I have seen your name. That's why I found the time and connected.
Oh, nice.
Yeah, thank you.
Thank you.
So we'll start. So good evening to all the participants. Uh, Welcome to Dr. Anand Mukhopadhyay to the our third day session of faculty development program sponsored by AICT. That is on future intelligent network towards 6G, and that is 5G and beyond with reconfigurable software defined radio and machine learning. So to introduce about Dr. Anand Mukhopadhyay, he's a senior engineer on the education team at MathWorks Bangalore, where he has been contributing since 2020. He collaborates with academic institutions and educators to enhance their curriculum and research initiatives. Before joining MathWorks, Anand completed his PhD in neuromorphic computing applications at IIT Kharagpur from 2015 to 20. He also holds an MTech VLSI design and embedded system from our institute, that is NIT Rourkela, from 2012 to 14, and BTech in Electronics Communication Engineering from Techno India College Technology. And he has authored and co-authored research articles in various journals and conferences. His interest focused on digital VLSI, HDL code generation workflows, and RTL in artificial intelligence and application. So I welcome Dr. Anand Mukhopadhyay for this particular section, and I thank him for wholeheartedly for accepting our invitation and be part of this particular FTP. Welcome, Dr. Anand.
Thank you, Hiramat sir, for the invitation and for the warm welcome. It is a pleasure to be a part of the sessions, especially when it is done by NIT Rourkela. So me being an alumni of NIT Rourkela, and it's good to see some of the alumni also joining this program. So before I begin, I see one hand raised. Is there any question, Mr. Ashish Kumar? Not audible. So am I not audible to others? I see one comment. Am I audible or voice
Yeah,
is
yeah,
okay?
yeah. I can hear you, Dr. Anand.
Okay. Okay. Then I see few comments from couple of the participants. Acha, so Gagan, you can just restart your teams. I think others are telling I'm audible. You can restart and see whether you're able to hear or change the audio setting. Okay, so today, let me begin then. Today, I will focus mostly on the AI aspects of wireless communication. Okay, and at the end, I will also show some of the things on the SDR which you can explore, because we have a lot of capabilities on the software defined radio front as well, and taking the theme into consideration. So you have both SDRs, machine learning, addressing 5G, 6G communication. So let me go to the slide deck. So Professor Hiramat already gave the introduction. So my background. So my technical expertise is in VLSI design. So I did my MTech in VLSI design from NIT Rourkela long back in 2012 to 2014. And thereafter, I did my PhD in the topic of neuromorphic computing applications, where I applied AI in some of the low power applications related to brain implants and wireless sensor networks. And after joining MathWorks, since 2020, I've explored multiple capabilities which I have never used when I was actually studying my master's or PhDs or bachelor's. Some of them are related to coder tools, HDL coder, verification techniques, and so on. So in this talk also, I will like to highlight some of those capabilities which you may not be aware of till now, but you could apply during your work in the domain of wireless communication and AI. So this is the journey from 1G to 6G communication. So long back, we were studying analog communication. We still study that, but after that, there has been a lot of importance given to digital communication techniques, because people are doing research in developing high-speed communication, especially if you see the three terminologies in the 5G space. So EMBB stands for Enhanced Mobile Broadband, and then you have ultra reliable low latency communication and massive machine type communication. So these are three things which are addressed by 5G technology. So we are looking towards more reliability, more speed of data processing, and how we can connect different systems. So when we talk about wireless communication, it is not just one technology. It is linked to many other technologies. So you can consider IoT as one of the other technology, Internet of Things. So which leads to examples like industrial IoT. So you have different industries where you have multiple machines. You need to make connections between those machines. So how do you do that? So you need a cloud framework, and you need to transfer a lot of data in a secure manner. Okay, so that no one can hack that. So wireless communication is clubbed with IoT. Then you have FPGAs, you have system on chip devices. So why it is required? So FPGAs can do faster processing. So whenever you have to do you have to do some processing at a higher rate, I would say, or a higher speed. Maybe design of a controller as a part of an overall system. You will need those kind of devices. So you need to deploy those things at certain places. So in fact, when we talk about 6G, we have something known as that RIS technology, right? Reconfigurable intelligent surface, which deals with some meta surface materials, and those things are like some of the research areas where people are working on developing some controllers for that RIS technology. So if you see, there are multiple technologies which are helping us achieve or helping each other towards addressing faster applications or addressing new applications. Okay. So another application which I can think of is in the automobile industry. So like automated driving, where people are focusing on making driverless vehicles. So it has been done in some places outside, but it's a very challenging thing to address if it has to be implemented everywhere in the world. And when we talk about that automated driving piece, it will have so many components inside it. One of the major components will be again communication, related to communication. So how do we communicate that large chunk of data, the video which is captured in real time, or the radar signals which are captured in real time. So there will be different sensors associated with the vehicle, and you need to communicate that data. You need to do some fusion between those things also. So it's not because such things have to be very much reliable. So you cannot just rely on one sensor like video or one sensor like radar. So there will be multiple such sensors, and there are things like taking the best result after understanding all those things and working on that thing. But that again leads to the application of automated driving in automobile industry, where communication is one such piece in addition to the other things. So coming to the general diagram which all of us have seen, whoever have studied communications, like we have a transmitter, we have a receiver, and we have a channel. Okay, so we are trying to send some data from one point to the other point. And in the era of wireless digital communication, the channel is the air, the wireless medium. But it will have so many obstacles, so many what we call that as noise. Okay, even if there is a building, it will get reflected from one building to another place. So we have to take into account all those effects in the channel. And there are standards. So there are bodies who define the standards, who define what will be the bandwidth allocated to different spectrums, whether it's 4G or whether it's 5G, and whether it's satellite communication, okay, where we are dealing with non-terrestrial networks, or whether it is Bluetooth or Wi-Fi technology and so on. So all these standards are on top of the base thing known as communication toolbox. So on the top right, you actually see these are the MathWorks products. Okay, so MATLAB and Simulink are the base products, and on top of it, we have things like toolboxes and block sets. So these are those toolboxes which will have the functionalities. So the functionalities which can perform these things, whichever you are learning in your theory. Then we have the radar toolbox, the DSP system toolbox, especially when we talk about software-defined radios. So what are software-defined radios? So basically, it is helping you to receive or transmit some RF signals, and instead of doing the processing or the physical layer processing of the RF signal on the board, you are making use of the computers. So you are doing the processing on your computer using computational tools like MATLAB Simulink, which is more easy to do, and then again you are able to transmit that thing. So that's why software-defined radios are so important, and different level of expertise. People with different level of expertise can explore that. Okay, the people having no knowledge on that can just use it to probably receive a signal just by giving the appropriate frequency, maybe a FM radio frequency like 98.3 FM, and try to hear that thing, see the spectrum of those things, and so on. And those who are working on the synchronization, advanced users, so who will be working on making the demodulation techniques or making new demodulation techniques, applying synchronization. So they will capture the signal and try to work in the simulation environment, how they can propose something new, something better on that. So that way, it's just another hardware. And this DSP system toolbox will have those functionalities. So people who are actually making those physical layer design, so they will be using certain filters which will be part of this DSP system toolbox apart from the other modulation things in the communication toolbox. Okay. Then we have two new things which are available in the internet outside the installation. One is known as 6G exploration library, and another is wireless network simulation library. So they have functions related to 6G as well as if you want to model a scenario of wireless networks where you have different nodes, different users, different base stations. So how the interference effects are affecting the communication. So all that scenario can be modeled using some of the things available in the wireless network simulation library. So after in the transmitter, when we transmit the signal, it goes through this physical layer, digital physical layer, and then there is the RF front end where we will have DAC, a digital to analog converter, will go through a mixer, power amplifier, and this front will also require some things related to the RF design. So we have capabilities around that on RF toolbox, RF block set, and mixed signal block set, where they talk about different schemes related to, you can say, serializer, deserializer, and so on, to model the RF front end. And for modeling the antenna, that is also a research area. So we have antenna toolbox, phased array toolbox, where you can simulate your antennas. You can give the shape, size, and the different mediums associated with antenna design, and try to see the performance depending on the S parameters and so on. After that, modeling the channel itself is a big thing. So most of the channel models associated with the different toolboxes will be there. So you can pick and choose from there. And then we go the reverse. So in the receiver, we are receiving the signal. We use a low noise amplifier and ADC, and then try to get back the signal through some digital front end and demodulation techniques. Okay. So on the hardware side also, there are a couple of things. So we talked about SDR. So SDR is a software defined radio. It's a hardware. And then there will be few instruments associated with it. So MATLAB and Simulink, they have a hardware support packages for multiple hardwares. I would not say for all hardwares, but at least the important ones you will find there. And if you install those things, you can work with those hardwares to either test your signal or measure the certain things. On the deployment side also, we support like FPGAs, SoCs, RF SoCs, and you can deploy some of the things which has to be which will run on those machines or run on those devices. Okay, so this slide actually gives you the overall view of what kind of products are required and where it is required. So you may be doing research in any of these sectors. So you will have more idea about the commonly used functions, commonly used applications or apps to build those things. But just to know the overall things, I went through this slide. So next, coming to today's topic, so we will be learning few things on AI. So what is our expectation for AI? So AI is, it says, from reactive to proactive to a predictive network. Okay, so when we are working on these algorithms without applying any AI, so we are in reactive mode. So we need the knowledge, the mathematics behind all these communication techniques, and we have to build those algorithms with some logic. Okay, and with experience, we will know like which techniques work better. So during that time, experienced communication engineer will directly use those blocks, okay, and try to work on some newer problems. That's the proactive approach. And the predictive approach will be when we are applying AI, okay. So it is depending on some of the things related to data. So if we can collect a lot of data related to some applications, we can predict some of the outcomes that we need. Okay. So the chosen solution needs to meet the performance, compute cost, reliability, and security requirements. So these are some of the things we need to take into consideration as well. So just because AI is a tool and it is widely used in many places, if we apply it, we need to see whether we are getting a better performance or at least a similar performance. What is the cost involved in using that? Are we saving on the cost? How reliable it is? Okay, and then comes the security concerns also. Can that system be not hacked or tweaked or so on? And with that motivation, we try to see what are the places where we can apply these AI techniques in the field of wireless communication systems. So here we see there are the user equipments, the base stations, a core network, and the app server. So a user is basically whenever communicating, the frequencies goes through a base station, and when we are applying these things on these local places, okay, maybe on the user equipment or on the base station, then it is a localized AI. We call that as a local AI. So we are applying AI for optimization of modulation. So how we can optimize the modulation schemes or source coding, channel coding, uh, equalization, synchronization. So these are all associated with the physical layer mostly. And then comes link level AI. So it focuses on the communication medium. So between two users, between a user and base station. So how we can apply AI in maybe estimating the channel, like channel estimation, okay, or prediction of future network conditions. So like that will fall under the link level AI. And then comes the end-to-end level AI, where we are applying AI in the overall system, okay, maybe to identify or predict some anomalies in the network operation, so suggest corrective actions, network slice management and networks. So it is more complicated because we are looking the system as a whole and seeing how we are applying the things. Now, complexity wise, it is very obvious that a localized AI will be less complex compared to end-to-end level, where we are applying AI to end-to-end system here. And in our with our tools, we have seen people have worked more on this first and two, the local AI and the link level AI, because of the functionalities that is there. Okay, so I would also say we'll focus on some of the demos related to the first two today and see how those are addressed. So coming to the next slide, so this is the typical applications of AI for wireless communication, the examples that we have. So let's see the first one. So it's on spectrum sensing and signal classification. So can anybody say what do we mean by spectrum sensing? You can use the chat window. You can use the chat window, or or you can unmute yourself and tell. What do we mean by spectrum sensing? I see one comment for white spaces. So Ravi Kumar, can you tell what do you mean by that? Channel to access without interference. Yeah. So that is.
Hello.
Yes.
It's a Gaurav this side. Sir, I think spectrum sensing is just to identify primary user and secondary user.
Just to identify the primary user and secondary user. Yeah, that is somewhat. But can you tell more on that? Like, how will you identify that? The primary and secondary user?
Actually, primary user are those which have allocated for that for utilizing that particular spectrum, and we need to identify the whole or the unutilized spectrum for those channels. Those have been allocated to the users, primary users, so that we can utilize them betterly.
Correct. So yeah, thanks for answering that. So I see another hand raised. Yes, ma'am. Rajeshwari, ma'am, you want to?
Sir, can you
Yes.
hear me?
Yes, I can hear you.
Sir, if any other, even though it is supposed to be like multi-access, if some other users are using, the spectrum should not be having any kind of others interference. Only one user or without any other people overlapping, you are supposed to use that spectrum, sir. And so we have to sense whether the spectrum is free or without any interference, whether that user can use it. In that way, we can transmit our own signal.
Okay, thank you, ma'am, for answering, and thank you, Ashish, as well. I think both of you have mentioned the same thing, and it's what spectrum sensing is. So to identify the spectrum, we need to sense that, and which user is using that, who is the primary user, who is the secondary user, so that we can avoid the interference. So that's a very important application in developing the communication system. So here, if you see an image here, right? So this is like a spectrogram of a signal. It is a time frequency graph. And if you notice here, so there is a frequency range on the left, the lower side, and the frequency range on the right. The left side represents the LT, the right side represents the NR, and there are some intermediate things as well. So from here, you can try to distinguish those things. So this becomes the data. So we'll come to some basics of AI after a while, but you think this as a data sample. Okay, so like that, if you have multiple samples where we are trying to understand the different spectrums, we can sense like which spectrum is used, which is not used, and which helps us to provide those, or which helps us to reduce those interferences. Then comes signal classification. So what is signal classification? Anybody wants to answer? What do we mean by signal classification? And yeah, thank you. I see many of you also answered about the spectrum sensing in the chat. Yeah, thanks for that. So I see what waveform is there on the received. Yeah, so that's, I would say, correct. So signal classification, we are receiving a signal and we need to understand, we need to demodulate that. So before demodulating that, we need to understand what was the modulation scheme applied to that signal. Okay, so if we can identify that, we can do the demodulation accordingly and get the signal back. So that is signal classification. Maybe mainly to understand what is the modulation technique. So how that can be done using AI. Okay, so we'll actually see this in our demo. So we'll do some hands-on thing. If you are in front of MATLAB, you can also try in a while. Then let's see another application, beam management and channel estimation. So would anybody like to say what is beam management?
Hello.
Yes. Yes, I can hear. You can tell. I cannot hear you now.
Sir,
Yes.
how to propagate the signal regarding the direction and the intensity? Suppose if it is going to be weak and attenuated, in that way, shall we take it, sir?
How to propagate the signal? Yes. So basically, I think you're right. So it is managing the you can
Field
say
strength.
related to the field strength. So what is the field strength and how you can maintain the signal or improve the signal to noise ratio? You can manage the things. So those things are related to beam management.
Yes, sir.
And channel estimation. What do we mean by channel estimation?
Whether the channel is supposed to introduce any noise or how that channel is behaving. Based on that, we have to make the signal to be changed. Or accordingly, we have to do the other end equalizing, and so we can have it. If the
Correct,
channel
correct.
is introducing so much of error, accordingly, we have to compensate. Am I right, sir?
Yes, yes, you're right. So we have to estimate, we have to know what the channel is. So if we know that, only then we can uh, uh, apply those inverse mathematical things and get the waveform. So whatever noise is there or whatever other components are there which is distorting the signal, we need to understand that. So that falls under channel estimation. So how we can estimate the channel? So that is also a critical thing. So using AI. So those things are also there. Then you see there are other applications. So for each application, we have examples like identifying the device which is used to communicate, localization and positioning, finding from where we are trying to communicate, digital pre-distortion, transceiver design, and so on. And in all these applications, somehow people have used AI and seen some significant results. So that's why it's a good place to do some research if you are want to apply AI techniques in these wireless domains. Now coming to some use cases. So after a few use cases, we'll try to see some demos. So let's just go through these quickly. So Coherent is a company who used MATLAB to accelerate the research on next generation AI for wireless. So they used a lot of the deep learning models, and they used tools like waveform generation, which helps you to generate synthetic waveforms of different types, whether it's 5G, LTE, or so on. And they also use SDR connectivity, okay, which can capture over-the-air signal for the testing part. So one of the quote by them is that the key benefit of MATLAB experience for the researchers is the breadth of hardware support, including USRP Pluto and Keysight. So the hardware support for these devices were very helpful for them, and the ease of use in the process from installation to visualization of their IQ data. It was easy to install, work with the hardware, and visualize those communication data, the complex data. Okay, so we'll see the hardware support packages today, and let's see the other use case. So NanoSebi, their challenge was to accelerate the design and verification of the RF power amplifier linearization algorithms, which is used in 5G and Wi-Fi 6 devices. So they use MATLAB to characterize the amplifier performance, okay, and develop pre-distortion and machine learning algorithms. Okay, so they were working on the design of the RF power amplifier. Okay, and they could also automate the standard compliant test procedures. So they reduced the development time by 50%, and they worked on that part. A few user stories from industries like Nokia and Qualcomm. So Nokia used the MATLAB tools. So it's from the China Shanghai team who developed an app. So they developed their own app for analyzing the 5G communication system, improving the collaboration between the teams and saving time. So there will be multiple teams involved in building the system. So they wanted to make a common platform so which everybody can understand. So they made a 5G communication analysis application where they can change certain parameters. Each team members can change certain parameters and easily get what kind of performance they are getting. So they use the MATLAB app designer, enabled rapid development of an intuitive user interface, saving this time between the different team members. Then coming to the Qualcomm one, they used MATLAB to develop 5G RF front-end components and algorithms at Qualcomm. So here the challenge was to support over 30 RF bands for 5G with waveform combinations 10x greater than LTE. So they used the MATLAB to model the transmitter and receiver paths, optimize for a range of waveform combinations, and enable waveform generation for customers. So how they can generate different waveforms out of it. So now coming to some basics of what AI is. So can anybody say, like, how many of you have already used AI in any of your work, whether it's communication or non-communication? You can raise your hands or type a yes. You already have some understanding of AI. If you have some understanding of AI, you can type yes. If you are new, you can type N. ChatGPT, yeah, ChatGPT is a product of AI. I would say it's a product of Gen AI, generative AI. So there are a lot of LLM models behind ChatGPT, and it is, you can say, one of the tools which is used among different industries as well to increase the productivity. So it can help you to learn certain things, help you to save your time in terms of doing some of the redundant things and helping you get some answers. It may not be fully accurate, but at least you will get some things very fast, and you can make use of those models. So any other tool that you have heard apart from ChatGPT? Anyone? Perplexity, yeah, that is another LLM tool. Napkin, okay, I have not heard that. Maybe that's another one. Crook, okay. Alexa. Alexa, I would say,
I'm not quite sure how to help you with that.
Yeah, so that's like a helping you towards building a smart system. Okay, I would not say that is like a LLM model, but it can help you connect to different devices. So it will be so it's like a smart assistant to you, who can connect you to maybe to a bulb, or to a smart bulb, to a smart refrigerator, washing machine. So you can do a lot of IoT related stuff using that. You can give them some command, and of course there will be some models inside it which is trying to process those things. So in that way, it's a product, it's a hardware product, but it will have some components inside it which is trying to understand those things. Again, the speech has to be processed, and based on that it will give you some results. So yeah, that's actually, it also has AI components apart from the other thing. Yeah, I see so many answers: Gemini, DeepSeek, Claude, Notebook, LM, Microsoft Copilot. Yeah, thank you everyone for uh, uh, mentioning all these answers. So now the challenge here, what you see, there are so many tools which are there and which are being produced every month, okay, for you to use to improve your productivity. Now the confusion is which one to use, where to use, how to use. So I would say whichever you're comfortable. So all these things are helping in the base level. They are good to see that all of you are aware of these things, which is helping you in your AI literacy. So how to use these tools to help productivity. But today, when I'm talking about these applications, I will focus a bit more on how you are using AI to address applications. So all these are the tools which have been made using AI. And again, this is helping you to get some answers, okay, get some predictions. So yeah, thank you all for the answers. Let me ask you another question. So what is machine learning? So we saw a lot of AI products or AI products which are there in the market, okay, and which everybody is using daily. But what do you understand by machine learning?
Hello, I am audible.
Yes, yes.
Learn from the data is known as machine learning.
Learning from the data is known as machine learning. That's absolutely correct. So
Yeah.
artificial intelligence is the superset. Yes.
Okay.
You wanted to say something else also? Okay. So that's correct. So
Yes, please.
whenever, no, I just thought you were wanted to add to your answer. Anything else you wanted to add?
ML is a subset of AI. AI
ML is
is
a
a
subset of AI.
technique and ML is a concept.
Hmm.
Yeah, so ML is a
Ye-
concept and AI is a technique. To the
Yes.
AI,
So
ML concept is a running.
yes. So that's correct. So ML is a subset of AI, and when whatever we are seeing these things, like whatever products you have mentioned, so most of them are a ML model, you can say, because we have used a lot of data to train those things. So whenever there is data involved and we are using that data on some statistical models, that is the field of ML. And inside ML, we have different types of learnings, like unsupervised learning, where we don't have the information of the label, or supervised learning, where we know the labels. So if we are doing a classification between a cat and dog, if we know this image belongs to a cat, this belongs to a dog, we have the labels, it's supervised. And then we have reinforcement learning, which is like interaction of the data with the environment. So there are some rewards given, some agents related to that. Then there is a subset of ML, which is deep learning. So which is exactly doing the same things, same kind of problem, but it is dealing with more complex problems. It needs more compute resource, and the models are more complicated. Okay. So today, the demos that we will look at will mostly cover models related to deep learning, and those will be of supervised nature. So you will know what the data is. You will have the labels for the data. So next, what I would like you to do, I will share you a link with you. Let me do that. Okay. Okay, I've posted a link in the chat. You can also type, you can open that link, or you can type AI for wireless communication plus GitHub. This is the first link that you will get. Okay. Yeah, I've shared it in the chat. Try to open it. And once you are in this page, you can open this in MATLAB Online. You can click on Open in MATLAB Online. Okay, so those who already have their MATLAB accounts, you can try to open it at your end. Others can observe. So you can just bookmark the link for your future reference, and you can see the demos that we are showing. So it will ask you to save the files. Okay, it will ask you to save the files. So I will also try to save a new copy for all of you to see. If it is asking you to log in, you have to just give your login credentials and try to save and open it. Okay. So here are the files, and currently this is MATLAB Online. Let me go to the first folder. And inside the first folder, open the first file, the work directory. So before we run that program, let me just give a brief of the demo. So when we are talking about AI-driven system, there are 4 stages starting from data prep, AI modeling, simulation and test and deployment. And in this example, we will try to do some simulation and test. So we will use a trained model. So we are not going to train the model or collect the data. We are just going to do some inference, and that also on a new set of data, on a test data. So we are not going to integrate it with a complex system or do some system level simulation. It's just testing of that data. Okay. And this is a structure of a neural network which is fully connected. Okay, it has input layers, output layers. So you need to give the data in the form of vectors. So you need to either do some feature reduction or try to depend. Each feature will represent one neuron. Similarly, if you are trying to classify something, depending on the number of class, you should put the number of neurons in the output layer. And these are the basis for many of the deep neural networks. The data can be of different types. It can be in the form of an image, which is like a matrix, or it can be a signal where you have it will depend on the sampling frequency and the value of those samples, where you can convert the signal to numeric vectors, or it can be in the form of a text where you are encoding the numbers or the text with some numbers, which becomes the pattern. So in the exercise 1, we are going to do some modulation classification. Okay, we discussed about that a while back. So if we are sending one signal with some modulated signal in the receiver end, how do you know whether it is a QPSK modulated signal or a different modulated signal using AI techniques? So that's what we are going to do. So you open the work file and let's begin the thing. So the first folder will have a work file, work getting started. So we'll open that and we'll start to run it. Okay. So you can click on this blue strip, which will run the first section, and you can see whether you are in the correct directory or not. If you're in the correct directory, you can continue. And second is you load the train network. So I told that we are not going to train at this point. So we have already loaded a train network, and we have some variables now, which were part of this modpred-network.mat file. So here we have the train network named as net. We have some receive frames, receive labels, and some classes. So let's see what is inside the receive frames. You can see we have 240 such samples, and each sample is a complex number with 1024 samples. So this is how the data is. And similarly, if you look at the classes, you will see there are 6 different classes of different modulation schemes. Okay, starting from 16 QAM to QPSK. So you got an idea about what we loaded. Let's inspect the network. So we are looking at the layers of the network. So it has like 8 layers, and it's a CNN. A CNN network is there. And we also see the same classes, the 6 different classes. Next, we want to classify the modulation scheme in the receiver end. Okay. So in the receiver end, you have to provide a test data. So what we are doing here, we are providing one sample which is randomly selected. So if I click on 64 QAM, it will try to select a 64 QAM signal. Okay, and then it will store in this mod frame variable. Okay, this is how we are able to visualize that data as well, the 64 QAM data in time frequency spectrum. And then we have to write one line of code. So this is the line of code that we need to write. So to determine the prediction, what the network is predicting. So we use a predict command, which needs the argument 1 as the trained network, which is net, and argument 2 as the test data, which is mod frame. Okay. Now, if I rerun this thing, this error will go, and we are able to predict the model or predict the class, which is 64 QAM with a score of 0.99748. So what is this 0.99748? Can anybody say what is this 0.99748?
Excuse me, sir.
Yes. Yes, Gaurav.
Prediction accuracy, sir.
Prediction accuracy, yes. That is the prediction accuracy. It is the score that we see here. So it is basically the probability. So
Classification rate, sir. Correct classification rate, sir.
correct classification rate. Yeah. So
Yes, sir.
I would say prediction accuracy is a better answer because suppose this value was less. So if this was like, you can say 0.6, okay, although it has a less prediction score, it will still be classified correctly. So let me show you how. So here we are able to see the score of each of the classes. Okay. And I've ran this program again. So it selected a different 64 com signal this time. Okay. And if you see 64 com is the second class. Let's see. And it has predicted this has 16 quam. So this is actually a misclassification. And why it is a misclassification? Because the first score is like 0.8 followed by 0.19, which is the second probability, and the others are almost or zero, you can say. So there has been a misclassification between 16 and 64 quam. So it's a 64 quam signal, but it has predicted as 16 quam. Okay, so that's a scenario that you will always get because AI models won't be 100% accurate. So let me run it again. And now again, you are getting a correct classification with a higher probability. Okay, on the third data. If I run it again, now it has predicted as a QPSK. Okay, so you see there is QPSK vector or the class has got the more score here. So it's again a misclassification. Then again, it's a correct classification with a lesser score. So like that, if you run this on different test samples and then aggregate all of those together, you will be able to get an overall accuracy, you can say. So how good it is performing on a larger or a more varied set of data. Here we are sending each data individually.
Excuse me, sir.
Yes.
Is this showing each and every iteration the different result? So it means we have not trained model batterly.
No, here that's a very good question. So we have trained the model, and here you are seeing you are feeding one data at a time. So this mod frame is selecting one such data out of this 240 samples. So there are 240 data you have. So it is choosing one of them randomly, and you are trying to see whether it is predicting it properly or not. Okay. So just by running a few samples, you cannot also say whether it's trained properly or not. You need to test it over all the samples, like all the 240 samples. That will give you the training accuracy, I would say. Then you have to test it over some unknown data that will give you the testing accuracy. So then you can understand whether the network is performing good or not. That's a very good question. And so am I able to make it clear what we try to do in this example?
Yes, sir, definitely.
Okay, so your question, I would think it will be answered when we see the second demo. So in the second demo, we'll do the same thing, but there we will do the training. Okay, we'll train the network, and we'll also test the network by sending a set of test data together. Okay, and see some confusion charts on it. Okay, then it will be. In fact, the observation from here is the network accurate all the time? So it was not accurate all the time, we saw by running it. And are there any modulation types that are being confused by the network? So we already saw between 16 QAM and 64 QAM, and as well as QPSK, there was some confusion. So how to see these kind of confusions in a better way, we'll see in the second demo. So there's a question from Neha, is the data random? So the data is randomly selected, but it's not random. It's randomly selected from this RX frame. So if you see, select test frame is a function which has arguments RX frame, RX labels, and modulation type. So if you provide the modulation type, it will try to pick one of the data samples belonging to that modulation type from the RX frame database. Okay, so it is randomly selected from this database. Okay. So now, before going to the next example, let me highlight a few things which we'll use there. So we saw this CNN network. Okay, so CNN are good for processing images, and if we are processing signals or test data, we go for LSTMs or RNNs. And it has layers like convolution layer, ReLU layer, and max pooling layer, and made it in different combinations. Then there are some hyperparameters. So these are known as filters. So suppose this is a handwritten character 0, and these are some filters that you have which are having different edges. So if you use these filters, so these patterns would be common in the number 0, right? So if one of the filters is, so we are doing some convolution operations. Okay, so each matrix is being multiplied and we are getting some results. And if there is some known pattern, it will train better, and you will be able to classify this kind of image when you are done with the training. Similarly, this image would not match well against the patterns for the number 0. Okay, this is good for the number 1, but it would only do well with this number 1. So we need to train and get these filter values, what we see, these patterns. So how will we know this pattern? So when we are doing the training, basically we are assigning the number of such filters, and these values will be the trained parameters for us. Okay, the kernel values. So this is just a very simplified use case where you just see black and white, and it can be represented by a low and high value. But when you are having actual image, there will be different range of values, okay, from 0 to 255. So how do you train these kernels? And then there is activation layer where activation functions like ReLU is used. Okay, so whenever you are processing certain things, it goes through activation layer. So ReLU is something which retains the positive number, and whatever is negative becomes 0. You can see the transformation here. And then there are some pooling techniques, which is basically shrinking the dimension of the network. So at the end, you are just classifying certain things, so you have to slowly reduce the dimension, so while retaining the information. So max pooling layer will try to see what is the size of the max pool. So if it is 2 cross 2, then within a 2 cross 2 matrix, whichever is the maximum value will be taken with the stride length. Okay, if it's the average pooling, it will take the average. And that's how you shrink the dimension of the layers. So this is the very basic things of a CNN. There are many other things which is made using these structures. And at the end, we have a fully connected layers, okay, which is like a normal network. We are sending the final matrix in the form of a vector for each individual neurons, and we again apply some softmax layer to turn the scores into probability and do the classification. Okay. So there has been some changes depending on the release on how the layers are used. So there was a classification layer before 2023B release, but which is not needed to be specified separately, but you do not worry about that. So if you are using the latest version, we'll see how you can work with this model. Then the question is, how do we know which layers to use? So when we are doing feature extraction, okay, for images, so there are layers like 2D and 3D convolution. When we are doing activation functions, so we saw ReLU, sigmoid, tanh. So these are the activation functions. So for sequence data, there will be a set of layers. For normalization of the inputs, there are techniques. So there are sections on which layers to be used while framing the network, and it is documented well with the guidelines when you want to create that network. So once the network is created, the second thing is to choose the hyperparameters. So hyperparameters are also the training options. So there are multiple hyperparameters associated. The important ones are the number of epochs or the number of iterations. So how long you want to train the network. And then the learning rate. What should be the so learning rate is basically the rate at which it is the network's error function is changing, okay, with every epoch, with every iteration. So if it is a higher rate, sometimes you will not be able to go to the minima of the loss function, and if it is too slow, it will not be able to train the network. It will take a long time. So you need to choose a correct value. So high function, a too high value will never converge to that minimum. A too low value, the loss function can get stuck into a local minima, okay, and you will not get the good accuracy. So you have to choose the learning rate properly. So you try to remember these two things: max epochs and learning rate are the hyperparameters. And in exercise 2, what we want to achieve is the same problem on modulation classification. Here we learn how to create and train the deep neural network. And on the right, you see an image. So this is the confusion matrix. So in the earlier example, we were sending one data. Okay, we were selecting that in random, and we were seeing whether we are getting the correct classification or not. Here we are sending all the test data together and plotting it in the form of matrix and seeing how many of them were correctly classified. So the diagonal, whatever you see in the diagonals, so it's the predicted class versus true class. So these are the correct classification. And there are only 2 misclassifications from this image. So in one glance, you get an idea how your network has been trained or it is doing. Important thing here we have used 960 samples for training, and we have used 240 samples which are being kept for testing this thing. So this is the confusion matrix for the test samples. Okay, so we'll use a 1D convolution layer for our modulation signal. So our signal is a kind of, it has 1, 0, 2, 4 samples, complex values. So we are considering those as 2 channels and the height as 1, because we'll try to send this in the form of a matrix to the 1D convolution layer. And number of observation is the number of frames that we have. Okay. So all of you, if you are open this, you can go one step back and go to the second folder. So this one, open the work modulation classification.mlx. And open the work. Yeah. So I'm typing clear. I want to clear the workspace from the previous example. And let's run the first section. So we are in the correct directory. We load the modulation data. So now you see you have the train frames, the test frames, the classes together. And we are choosing one of the frames from the train set, sample frame, and looking at the different variables using the whos command. So if you type whos, whatever variables are stored, loaded in the workspace, you can see the dimension and the bytes and the type of those things. In the next section, we'll view the data set. So we use a helper function, plot spectrogram. So if you want to know how this function is working, so these are user defined functions which are kept inside this helper files folder. Okay, so it is basically sending the arguments like the train frames and labels and giving you the spectrogram plot, okay, for all the 6 modulation schemes. Let me see if I can show you sidewise. So you can change the output view. You can send it to the right, or you can just see it at the bottom. And after that, we'll open a deep network designer with a partially created network. So this is how the network will look like. It will start from a sequence input layer. So let's open this. Okay. So on the left, you see the sequence input layer is, you can just drag and drop it here, and a conv 1D layer. Connect this here. Then the important thing is to change the block parameters. Okay, so these are the default parameters that you have. The input size is 1, the minimum length is 1. Okay, but we know the length of the frame, sample frame, is 1024. So we have to specify that. And there is a provision to split the complex input. So that's the complex data. We'll do that. Then we'll go to the conv 1D layer, and here are the options. So we have to give the filter size as well as the number of filters. We'll choose a filter size of 8 and number of filters as 16. So why we are choosing this? So we'll come to that. So just remember, we change the filter size to 8. Okay. And after that, we can just analyze the network. And it says it has 2.4K parameters, 8 layers, no warning, no errors. We can export the network to workspace. Okay, under the name net_1. So we have exported the network, and the same thing could have been done using command line codes as well. So in that case, you need to create your own layers like this. You have to mention the sequence input layer, the con bundle layer, and the other layers. And you are sending these two parameters, SPF and SPS. So samples per frame is 1024 and samples per symbol is 8. So that's why we chose the filter size as 8, and the number of filters should be a power of 2. That's why it is 16. So the SPS value is 8 here, samples per symbol. So you need not run this. We have already exported the network, and you have also analyzed the network. So next is the training part. So we will see how we are going to train the network. So here we can specify the maximum number of epochs. So let's see the maximum number of epochs to 150, and mission learn rate 0.01. Then there are options. The training options are already given. Some of the default ones are mentioned. Let's run this. So it's taking some time to okay. All right. So now what we did here, we defined the options. I thought I already ran the training command. So we have that's in the next section. So this is the train net command. So which will start the training. So we need to provide the arguments to it. So let's do that. So the argument one is the receive train frames and the labels and the variable name for the network architecture, which is net_1. Let's see all the other things are there. Now let's run this. Yeah. So after you run that command, it will show you the training progress, and you can see how the training accuracy is gradually changing. So it started from like around 10, and it is now over 80, and it's still and okay. The desktop MATLAB has a better view for this, I've seen. So here you cannot see the entire thing. Or I can zoom in, zoom out. 1 second. So although you can see the numbers here, so how the training accuracy and the loss are changing, and the final graph. So this is better to see. That was not a very nice way to visualize the training process. But anyways, we can see it here. So how the accuracy is increasing and the loss is decreasing. So this should be the trend. So if it is not following this trend, probably you have to stop the training and try to change these two hyperparameters at least to start with. You have to select the correct learning rate, and you can change the number of epochs. And after that, you are going to evaluate the network on a set of data. So here we are using this mini batch predict, and we are sending the test frames and the trained network. Okay, so this mod pred network is the trained network now. So let us do that. Sorry, mod pred network, and receive test frame. Then it produces the test metrics, and it will give us the test accuracy for all these test frames. And you are able to see the confusion matrix at the bottom, right? So again, here you see there is misclassification between 16 and 64, okay, which we were seeing manually in the previous example. So 16 QAM, 12 times it has been, it's a predicted class, but it was a 64 QAM, so it's the misprediction, and the rest are okay. Okay, so we got the misprediction here. And as further exploration, you can try to optimize the hyperparameters. You can change the network. You can change the number of filters. We chose like 16 filters, filter size, optimize network structure, add more layers. So these are things to explore, so that maybe you can try to improve this or not. So that is one thing. And there are some references out here. So this was the second example. Now we are close to 7:30. Let me summarize what we did. So we did a example on modulation classification and using a pre-trained network as well as we trained it. We used CNN as the network, and we used the spectrogram as the image. So we represented that IQ data in the form of a 1D image, and we sent through a 1D conv layer. And like that, there are different types of time frequency transformations. So like starting from basic spectrogram, wavelets, or other transforms. So you can try to explore these transformations as well if you are getting better results or not. So we have seen that complex signals can be fed into these deep learning networks, and we can design, import, and visualize the deep learning networks interactively using the DND Deep Network Designer app. And hyperparameters are the parameters whose values control the training process. So can anybody say what were the two hyperparameters we used?
One was epochs.
Epoch, yes. One was epoch and other was?
And the learning rate.
Learning rate, yeah. These are the two hyperparameters we used. So yeah, thanks for answering. So next, what I would like you to do is, so we covered two aspects. We did the AI modeling where we tried to train the model as well. So we did some training and we did some testing on that data. But then from an end-to-end point of view, there are other steps. So if you are working on the data preparation part, you can make use of the wireless waveform generator app, which will help you to generate synthetic signals. So you need to give the frequency range, the parameters, and generate those signals. For more testing, you can make use of SDR devices, Bluetooth devices, which can help you to transmit or receive signal and test on those data. And there are deployment workflows as well for advanced RFSoC boards as well. Okay. So we support like all the main SDRs like RTL SDR, Pluto SDR, and USRPs. So you need to install support packages for that. This is just showing you brief of the wireless waveform generator where you are choosing the FR1, FR2 frequency range, the modulation coding scheme, and the reference channel. So all the information that are required before you can generate that and see the spectrum of that signal. You can add some impairments and all those things. And once that is done, you can export that as a form of a function, okay, which will help you to generate those signals. So that is another way to work on the data. So we saw this DND app today, and there is another app known as Experiment Manager. It will come later if you want to fine tune the hyperparameters. So we just changed that manually. So this will do it automatically. You have to just give the range of the hyperparameters, whether it's learning rate and so, and it will try to give you such results over a few days of training. Okay, so this is for fine tuning your hyperparameters for deep models. Then on the system design, you can also export some of the things in the Simulink framework and integrate with complex systems. So we took two examples, but yeah, and in the two examples, we used the pre-trained network and we also applied some transfer learning to retrain the model. I would ask you to explore the channel estimation problem. So there is a third demo as well, which is solving the problem of channel estimation. So you try to explore that in the tool. And as a summary, these are the things you can also try to, if you have a SDR board at your end, you can explore those things. Another thing in terms of resources, I would say there is a website on teaching wireless communication, which focuses on a lot of resources on wireless antenna RF, prototyping SDR, and AI for wireless. So this is a one page which will give you a lot of resources. There are some course resources which have been uploaded by faculties who are working on teaching this every day. You can get some good modules to work on these topics. And there are some self-paced on-ramps like deep learning, machine learning, wireless on-ramps in the MATLAB Academy page, okay, which could also be used. So with that, I think we are over 7:30. So I would ask you to Let's take some time to fill this feedback form, and you can ask any questions that you have for today's session, and you can contact me over the mail ID. After the session also, if you have any questions related to these or any other technical topics, I will be happy to answer that. So any questions at this point before we can start with the next session? I can take a few questions if we have time.
Anand, there is a one question saying, share some application of LSTM in communication.
Application of LSTM in communication. So LSTM in communication, then we have to, LSTMs are good networks which can process the sequence data, okay, the time series data. So if we have data in that format, we can use LSTM networks as well. So in this case, we used CNN where we were sending the spectrogram, which is like an image to that CNN model. So in that case, we would do that spectrogram kind of transformation. We'll have to see how we can send the time frequency, send the signal data directly, the sequence data. So there we can apply LSTMs as well.
One more question is, could you share the links on demos related to channel estimation?
Links and demos to channel estimation, yes. So in fact, let me show you the third module here is on channel estimation. So you have a work file. So I would ask you to go through the work file and try to fill in the gaps. So most of the things are there. And if you face any error, you have a solution file as well with the complete code. And it follows these references. So at the end, you will be able to estimate the channel, okay, through a conventional method, linear interpolation method, the practical estimator. This is the conventional method using neural network, and this is the actual channel. So how you are closely able to estimate the channel using a neural network, okay, and this is the error value, okay. It is also kind of lower than the practical estimator. So you'll be able to do it on a OFDM symbol. Apart from this, if you can find more examples, so I would say teaching. So you type this thing. This is the web page. You can start with this page. And like I was telling you, you will get different resources. So you can go to these resources and you can find different.
ఓ నేను చూస్తలేను క్లాస్ వింటున్నాను ఇటీ రాసేస్తుంది అర్థం ఒకటి అర్థం కాదా ఈ ఋషికి ఆన్సర్ ప్రాక్టీస్ చేయి ఫస్ట్ క్వశ్చన్ చదువు నీకు అర్థమవుతుందా క్వశ్చన్ ఏదో క్వశ్చన్
I think somebody speaking and
Yeah, that is muted.
Okay. Yeah, any other questions?
Okay. There is a one question saying that any certification course for UG students, MATLAB toolbox for adaptive beamforming 5G massive MIMO.
MATLAB. So the toolboxes are basically the communication and 5G toolboxes from which the functions will be used. So you can find the examples. So first of all, let me show you the course for the UG students. So matlabacademy.mathworks.com, it has a course on wireless communication on-ramp. So UG students, if you give this as an assignment, they can complete it, and it's like a 1-hour course. They can submit the certificate signed by the Director Training Services with the completion ratio to the faculty members. So that way, they also learn some of the coding schemes, okay, related to this topic. So there is a content for that. Second is the documentation page is very useful. So let me show you wireless communication plus MATLAB. So that is this solution page. So today we were talking about AI for wireless. Let me go here. And here you are finding those examples. Okay. So like spectrum sensing, modulation classification, data synthesis for 5G channel estimation, and so on. So if you go to any of these examples, you will find this example. You can copy this command, you can open it in MATLAB online, and you can also see which are the toolboxes used. So it mainly uses 2 deep learning and 5G toolboxes for solving this example, and you can run it in your MATLAB window. So if you are having a desktop version, you can just copy paste this, run this thing, and it will open the example for you. So the example is here, and you can go through the example. Okay, any other questions?
Yeah, there are lots of questions.
Okay.
I think Professor Deshmukh has joined.
Okay, then we can, Ajay, I will just share the over the chat my mail ID. You can reach out to me.
Yeah.
I will try to reply to your questions offline. Yeah.
So once again, I thank Dr. Anand for giving a very practical and that is a hands-on session on MATLAB with that is AI for wireless application. So many people were having a lot of questions, and he could answer all those questions. And thank you very much, Dr. Anand, for your nice and wonderful session.
Thank you, Professor Hiramat. Yeah, thank you everyone for your attention, and yeah, I hope you have a wonderful next session and followed by the complete FTP. Yeah.
Thank you very much. So our next session would be by Professor Siddharth Deshmukh. So I would request Deshmukh sir to take the session. I think Professor Deshmukh. He has joined. So sir, good evening, sir.
Yeah, good evening, sir. I'm just sharing my screen.
Yeah.
So is my screen visible?
Yes, sir. Yes, sir.
So can I start the talk, sir?
Yes, sir. 1 minute. Just I will introduce and
yeah, you can introduce me first and then.
Good evening, participants. Our next that is lecture will be by Dr. Siddharth Deshmukh. Sir, welcome to the Faculty Development Program. Thank you for considering our invitation. Sir would be delivering lecture on Age of Information, metric for timeliness in the next generation communication system, so which is a very novel topic. So briefly, I will introduce Dr. Siddharth Deshmukh. He is presently associate professor with the Department of Electronics Communication Engineering at NIT Raipur. Chhattisgarh. Before joining NIT Raipur, he was our colleague as an assistant professor with the Department of Electronics Communication Engineering, NIT Rourkela. While being a faculty at NIT Rourkela, he also worked as a postdoctoral research fellow with the Intelligent Signal Processing and Wireless Network Center, Department of Information Communication Technology, University of Agdera, Norway, under the guidance of Professor Balster. He completed his PhD degree in May 2013 from Department of that is Electrical and Computer Engineering, Kansas State University, USA. Before pursuing that is doctoral research, he worked as a research scientist at the Center of Development of Telematics, that is CDOT, Bangalore. And he received his MTech degree in telecommunication technology in the that is telecommunication technology and management from IIT Delhi in 2006, and he obtained his BTech degree from electronics communication engineering from NIT Raipur, where presently he is faculty there. And his research interest lies in the signal processing and wireless network. Sir, I welcome you to the this faculty development program, and I request you to take this.
Okay, thank you, sir. Thank you very much, sir. Good evening to everyone. Just to confirm, are my slides moving or is it stable? Just want to confirm. When I'm changing the slides, is my slides changing in your screens?
Yeah, they are changing.
Okay, that's fine. Because sometimes it gets stuck, so it's an issue. First of all, there was a very nice talk which you were listening, like use of AI for wireless communication, and many of us, like nowadays, are using AI in our research, and somehow, like the center of attraction is like this AI, and I hope like most of you have got a lot of like the previous talk might have answered a lot of questions and queries. In this talk, probably we will be moving a little bit more on metric. Okay, when I say metric, means some way of seeing how the communication system is performing. Probably one more thing, I apologize for that. The date written down is June 10, 2025. Somehow the date didn't change. So I apologize for that. So, but coming back to our topic. So topic is more about age of information metric. Okay. This concept of age of information is like probably I will say when I was doing my postdoc, during that time, it was almost coming to the wireless communication networks. But this topic is almost a 10 years old topic. I would say it is not a new topic. However, maybe because of the new applications in IoT and real-time communication systems, there is a lot of attraction or research focus on this topic. Okay? So probably I thought like it will be a very nice thing for many of our faculties and researchers to know about this. So this is a brief content. Like I was first talking about 5G communication and then why this AOI metric is important in the next generation communication systems, core concept and some research work which we have done. After this, I will be moving more towards something which is we are doing as a research lab recently, where we are using AOI metric for channel estimation, okay, or for characterizing the quality of wireless channels. So this is something which is like a novel work on, like we can say, like something which is not being done outside or for any other research area. So we have introduced some of new concepts. So I will cover that also. So if you come to the 5G networks, many of you might have seen this picture. I have taken it from one of the research papers. And this essentially gives us an idea why 5G is different from 4G network. If you go back to our history of generations of our wireless networks from 1G to 4G, if you see, like previously, like previous generation, the focus was more on voice, and so slowly it went to the like in 4G, it was more on a data. Like even the voice or LTE was something like we are talking about voice being packetized and sent through the wireless network. So everything became data. Then the question arises like, what next? And in the 5G, if you see, the next thing is coming to the different applications. Okay, so 5G network is not just about giving you a quality of service to have a good video call or a good gaming application, but it's more about catering to the needs of diverse applications. For example, if you see in this figure, you can see there's a smart city. Okay, there's like smart city, smart homes. So there's lots of IoT network is there. Apart from this, you can also see you have autonomous cars. Okay, so autonomous cars have their own requirement, like in terms of latency and all. And then you can also see, like you can have, nowadays we're also talking about low mobility large cell networks. Okay, it's something like in which like people are working on it. So like you can see, like nowadays the focus is not just on one application but diverse applications, and diverse applications have their own different quality of service requirements. So how a given network can provide services in these different applications. Okay, and that's where the 5G is arranged. And if you see the 5G architecture along with network slicing and all, you can see like and you can see numerology. Like if somebody is studying about the 5G architecture, you will get to that part where this numerology concept and introduction of network slicing, all these are trying to give different quality of service in terms of throughput and delay to different services. Then if you see like, okay, if you try to broadly classify the types of applications, right? This is a ITU release 2015. Then like you can see like 2015, it was perceived what 5G will provide. So you can see in this is called as the service triangle. And if you see the three vertices, where we are talking about in the top, like top is the one which we use, like enhanced mobile broadband. For us, like our mobile phone must do everything. So for example, a mobile phone must give you very good video quality for chatting, and we must give a online gaming application and seamless connectivity. So high speed mobile broadband is there one, like mostly as a commercial users, we use it. But apart from this, if you see the one side of our triangle, we're talking about machine type communication, massive machine type, MMTC, massive machine type communication, where we're talking about connectivity to large number of sensors. So these sensors may be deployed in agricultural field. These sensors may be deployed in, for example, mining area, or sensors may be deployed in, for example, industrial IoT point of view and all. Okay. And if you see the last triangle, you have ultra reliable low latency type of communication, where we're talking about self-driving cars or mission critical applications and all. So you can see on one edge or one vertex, we are talking about giving high speed. Other vertex, we are talking about giving a connectivity or simultaneous connectivity to large number of devices. And one type we are talking about that the packet be delivered with a very, very low delay or latency. So if you see, well, if we just focus on the latency, because this is more of an age of information topic here I'm covering on. So you can see age itself means somewhere we're talking about time. Okay. So as far as the 5G and 6G standards are concerned, they talk about ultra reliable low latency communication, which is something like you must be able to deliver the packet with almost, it's like 99.99%, almost 100% reliability. Along with that, we are talking about the packet must be delivered within 1 millisecond. Okay, but this is the latency. Okay, and if you see, latency is an end-to-end parameter. For example, when we talk about latency, let's assume we are talking about there is like a layered architecture at the base station and layered architecture at the mobile phone. So how much time a packet starting from one layer reaches to the same layer at the destination? Okay, that's the delay or the latency. And probably like currently the solutions are like, if you want to guarantee such a small latency, you must be able to predict how much, because there are diverse application, you have to provide resources, right, for ensure that latency. Then this is like solutions are more about like knowing in advance where the next packet will come, or like how the variability of the network is there and all. Okay, so but along with that, there was a need, like researchers, when they started working on this part, they thought about, okay, let the packet be delivered to the destination, but what about if the packet is time critical packet? When I say time critical packet, means that packet, for example, let's assume you have got a temperature data. Okay, very simple thing. I have got a temperature data, and I want to do certain signal processing on that temperature data. So, but the processing is somewhere done in the cloud or in the like remote server. And I somehow when I take the packet, okay, as a critical packet somewhere, like you can think about, there is an industrial plant and there is a big thermal unit running on, and I'm taking the temperature data and I'm doing certain processing in the remote server. So the temperature data, okay, it is, let's assume it is taken at some, for example, right now the time is almost 7:56, and that temperature data was taken, let's assume, half an hour back. Like it was started, like the temperature data was taken at 7:30. And by the time, because of the queuing delay or because of the congestion in the network, it took somehow, worst case, it took a lot of time to reach to the remote server. But then remote server, when it reaches it, it is of no use, because, for example, if it is some critical application going on, which needs like a control action to be given, maybe in a minute or something, already that packet is quite old. Okay, I'm giving a very worst example, but when you're processing a particular packet, you must know when this packet or information was generated, how long it is. Like, is it very old? Should I work on that old packet, or should I think about how can I get the recent packet or the latest packet? Okay. That's why the quantity of freshness of data came into picture. So one can argue, or when you, like, if you're a communication engineer, you can think about, okay, sir, that's okay, but what's wrong with our existing metrics like delay and throughput? The problem with these two metrics, as I told you, delay is an end-to-end metric. Okay, it's just between it is written down here, measures the time interval between arrival of packet and its delivery. Means, like, for a layer when the packet arrived, and in the same layer the destination when it delivered, it is the metric. But and throughput is determined the successful, like what is the rate of successful transmission. These two metrics, for example, even if you increase the throughput, there's no guarantee you are delivering the fresh packet. You may be delivering the stale packets which are already there in the network. You're not discarding those bad packets. Or even packet delay, like delay is also, you can minimize the delay, but delay minimization doesn't guarantee anything with the queuing system. Okay. So considering the different real-time applications like emergency scenarios and vehicle-to-all communication, and lots of new drone type applications and all are coming up, the concept of age of information is, like as I said, it has attracted a lot of attention. And then the point is how we, like you can see this in this slide, I'm talking about lots of applications which can be there for this AOI metric, where we are talking about tactical communications, or like where we want to, maybe a defense or something, like where we want to send secure and high data rate. It's a real-time data rate, right? In emergency scenarios, for example, let's assume there's a fire in some big building, and somehow there are fire responders, or first-time responders we call them, where they want to save life. But let's assume in a particular location they get information that there are some people lying there, but that information was 10 minutes old. But which means by the time they arrive, probably the casualty has already happened. So once again, this is a very critical time, and every second, like you can say, minute counts. So there also you need to ensure that the packet, the time it gets generated, it must deliver to the destination. So you must know what was the age of that packet. Same thing with the autonomous vehicles or federated machine learning. All these things require the like we can find age of information has a very good importance impact. Give me 1 second. Okay. So how we measure the age of information? Age of information. Okay. Sorry for my kid who was at the back. Okay. Okay. 1 second. I just switched it. Okay. So how we characterize, like how we define age of information. So because t is, like if you see, we say at is equal to t minus yt, where t is the current time instant and yt is the time at which the packet was generated. Okay, so the time elapsed from the current time to the time at which the packet was generated is defined as the age. Very simple definition. And age or AOI depends upon the packet delay, like how much time how much time is required to deliver that packet, and also depends upon the inter delivery time. Essentially means, for example, it accounts for queuing delay and all. And to ensure the quality of service with respect to AI, the scheduling of packets, like which packet to send and when, is a very important thing. So most of the works have worked on, we have worked on scheduling. And I too, when I started my research as a postdoc, along with one of the research scholars, I started with this metric. And this sum up part, which will be explaining here, will be a part of my postdoc along with my, I'm working with the PhD scholar, so I'll explain it. So if you see AOI minimization, is a very simple example. Let's assume the packets are generated. Like if you see time instant T1, the dropping down arrow shows the time at which packet is generated. So age, because even though it is generated, it's not delivered at the destination, the age increases. The moment it is delivered, age reduces. Then once again, age increases till the next packet is delivered. So the time at which it is delivered is more important. Okay. And then when we talk about the wireless networks, so see why it comes to the wireless networks is a more important thing, because wireless networks are the last mile connectivity, we call it. There, we all know our wireless channel is not a friendly channel. Okay, there's lots of packet drops and all, and as the number of users and devices are increasing, you have a lot of queuing delay also. Okay, so somehow we need to ensure that this last mile connectivity brought by 5G or 6G networks, they must be able to cater to the needs of the AOI metric. Okay. So that's where this research goes, and we are going to talk about the cross-layer optimization. When I say cross-layer optimization, means we are talking about optimization where MAC and file layer. Okay, file layer will ensure how much power must be radiated out, like power of the symbols and all. And MAC is more about which packets to schedule, the scheduling and the power allocation. So in this connection, we are going to talk about today, like at least we all know, when you have multiple users, you need to have multiple access technique. And one of the recent multiple access techniques are NOMA, non-orthogonal multiple access technique. So if you see in this diagram figure, you can see a base station. It is serving the two users, user 1 and user 2. The normal mode of communication, which is still existing in 5G or even the previous generations, it was more about TDMA or FDMA or even OFDM. Okay. So what is there in the differences? Like all these are called as orthogonal multiple access techniques, where, for example, in TDMA, you give one time slot to user 1 and then next time slot to user 2 and go on doing this. Or in FDMA, what you do is you break down the bandwidth into subbands and allocate one subband to user 1, other subband to user 2. OFDM, the subbands are orthogonal to each other, or the subcarriers are orthogonal to each other. But then the point is, if you have a large number of users and due to scarcity of bandwidth and all timing constraints, why not to must the users or multiplex the users in same time and frequency? You can see here we are trying to serve the two users in the same time and frequency. Then we all know there will be interference. User 1 and user 2 are going to interfere with each other. But in NOMA, the way they ensure that the two users like are separable is in power domain. Like it's like a power domain multiplexing where one user will be having lower power, other user will be having higher power. So if you see the figure, the base station one user is like user one is nearby to the base station, user two is far away from the base station. And if base station, for example, if it's doing some, for example, considering the user two is far away, okay, then he will allocate more power to the user two because of the large scale fading. User two will have more power. User one being nearby will have a allocated less power. So what's going to happen is, for example, user two, when because of the interference, the user two is also going to receive the signal of user one. However, user one signal, the power was less because being nearby. So user two receiving along with user one signal, but it will be weak because that signal has to travel to a larger distance. So user two will receive the user one signal, but the intensity of the signal, user one signal will be very weak. So interference is very weak. So it can decode, you can consider that interference as noise and decode its own signal. However, for user one, you can see like because for user two, it was radiating with more power. So user one will receive the interference with very much significant interference. So what we do is we call it SIC, where we first cancel the interference. Like what we do is we first decode the user two signal, then it cancels its impact, and then once the user two's interference is cancelled, what we do is user one will decode its own signal. That's called a successive interference cancellation. Like before decoding your own signal, you decode the other user signal and then cancel its impact and decode it. So okay. So here we can, what you can see is like multiple users can communicate in the same time and frequency. Okay. So this is the multiple access scheme which we were using for AOI minimization. So in this context, there was also like, for example, I talked about only two users. Normally, you can see like if there are more than two users, the SIC will become more complex. So in considering that, normally two users are considered. But if you have multiple users, what you can do is you can group them. Like for example, what we have done here is like there around, you can see there are 5 users. Okay. So at one time of what we are doing is we are grouping them. Okay. But sometimes if the users are nearby in the same location, or like if they're facing the similar channels, then using NOMA is not a good technique because successive interference cancellation fails. So in that regard, you can use OMA. Okay, so for example, so here the point is, can we use NOMA and OMA in a hybrid way? Like sometimes I'm using NOMA and other times I'm using OMA and then still providing the proper quality of service. So, model overview, for example, we are talking about single access point. Okay, this is this is like what we are considering. We are trying to minimize the long-term time average age. Okay, like we want to minimize the age of metric. We are ascertaining like the energy efficiency is there, which means we want to radiate less energy, and we also want to ensure the robustness, like the rate requirements for the users, like they must be able to reach their, like the packets must, like service quality in terms of throughput must be maintained. So with this, what we did was, like if you see in this figure, it's a very important figure from understanding point of view. Here you have 3 users, right? And there is always the option of grouping the users, maybe in terms of NOMA and OMA. So if you see here, that like the top one says the arrival. So you have the packets are arriving in the first slot. Then in second slot, you are like only like the pink and the purple users are being delivered the packet. So their age, if you see, the age drops for purple and pink. However, for the green user, its age is increasing. But then once the green user say packet is delivered, its age drops. But for other users, the age increases. So it is like whenever the packet is delivered, the age will reduce. Else it will go on increasing in the linear way. So here we considered once again imperfect CSI, where we know the statistical knowledge of the channel, right? Then and user equipment, since they have to do the SIC, we assume they have perfect CSI. So here we form the, like for example, as I said, in general, we can form the group, and theoretically, NOMA says you can form as many number of users in the group. But considering the practical situation, we consider only 2 users in a group. And for example, if you have 6 users, for example, if you have 3 users and you can the group size is 2, then you can have 6 virtual groups, which essentially means either you can allocate that resource only to user 1, 2, and 3, which is essentially G1, G2, and G3 indicates the OMA. Or you can club them together. For example, 1 and 2 are grouped together, 1, 3 can group together, or 2, 3 can be grouped together. So it is like, depending upon the channel scenario, you can work with OMA or NOMA. Okay. Then, as such, as I said, we want to minimize the age of information. So we formulate this is an optimization problem. You can see like here, we are trying to minimize the time average. This is like over the time. It's not a instantaneous minimization. It is a over the time we want to minimize the age. Okay, and it's like a age of the network. We have a constraint, like as I said, we want to ensure the energy efficiency. So we want to ensure that over the time my transmit power is less than the P average. Also, we must not radiate beyond the limit. So because this is a on an average constraint, this is more about saying like, okay, instantaneous power also must be below the radiation limit or Pmax. Then we're talking about the, because since the channel is imperfect, we're talking about that the probability of success must be greater than a particular threshold. We must not transmit a packet with a very low probability because that packet is already going to get lost. So we must always ensure like the particular success probability is maintained. And then this last constraint is more about at a particular amount of time, only one group, right? When I say group means these virtual groups, either user 1 will be allocated, user 2 will be allocated, or a group of users will be allocated. That indicates the which group you are going to select for transmission. So to solve this, this we call as a sequential decision problem. Okay. And here I will tell you, like in general, whenever we talk about such optimization problems, some of you might be familiar with these things. Optimization, we can either use, there are 2 approaches at the moment. One is called as Lyapunov approach, okay, where we are see these are like, if you see this is a, this problem is of as if I am minimizing the age along with I have a constraint of power over the time. So what you can do is like as if you consider minimizing the drift as if on an average I must be always near to the average P average power while minimizing the this is called penalty where I want to minimize the age. Okay, or we can also go for something called as Markov decision process, okay, MDP. So I will give a brief idea of both of these techniques because we have used in one example I have used the Lyapunov, another example we have used the MDP type of thing. So as I said here, like if you see, if I want to manage my power, I must not drift away from the P average power. So that drifting is managed as if there is some Q. Q means I want to always ensure the Q must be very small. Means I want to always ensure that whatever I am radiating on an average must be close to P average. Okay, so that's essentially is called as the queuing backlog. And penalty is more about, because when I'm trying to ensure P average, there is like it is possible the age may start increasing if there are contradicting things. Then in that case, I want to act as a penalty. Look, okay, if you are minimizing the backlog, you must also have a penalty on the age. So I want to minimize both the penalty and the drift. So that's where the things are. So this is how the age changes. For example, if packet is not successfully transmitted, age increases by 1. If it's successfully transmitted, age resets to 1. Okay, why? Because if packet is successfully transmitted, means that it was generated previously and just now you transmitted, so age will be 1. Similarly, as I said, we have formed virtual queue. You can easily see what we are talking about is this is a transmit power minus P average. So what is the difference between them? So we have this, like we have normalized this. So if PT minus PX is like if we are close to the P average, then this will be 0, and so the Q will be stabilized. Okay, that's what it's the meaning. And then here we have found changed the objective function where we are trying to minimize this called as the drift, and this is the penalty term. Okay, so this is called as drift plus penalty, and then this becomes optimization problem where I want to find out the transmit power and which group to allocate such that I'm minimizing the drift plus penalty. Now, so this is now a single time slot problem. Previously, it was a sequential decision problem. Now it has become a single time slot problem. And then the point is, like, if there's those who are aware of optimization, they might know, even if we have got a optimization problem, then also to find a solution, sometimes it's easy, sometimes it's difficult, depending upon whether the objective function is linear or convex or non-convex and all. Okay. So here the problem, if you see age is a function of u, and you have also power which is related to the success probability and all, this is a non-convex problem, and to get the solution is difficult. Moreover, selecting a particular group is an integer problem, so it becomes a mixed integer nonlinear program. So to find the solution, I will not go in deep for that, but what we have used is, like, we have broken down the problem into sub-problems where as if we are solving it for either for NOMA, OMA and all. And with that, there is a certain approximation techniques which we have applied, and we have shown that the solution is now, like, within the, like, we call it polynomial time solution we have obtained. So this is the performance which you can see, like, with our proposed algorithm, we compared with the state of art for the 2 users. Some people have just done it for 2 users, and we showed, like, okay, the proposed solution is like minimizing the average age. Like, there's a considerable improvement compared to the state of art. Same way for if we have multiple users, like more than 2 users, there also our proposed solution was performing well considered to the state of art. We also showed, like, because we are talking about energy efficiency, so what is the performance if we have different energy efficiency, like 20% energy efficiency, 50%, and 80%, and we have shown, like, in our solution is like fairly well, like, in all these categories. Coming back to the solution, as I said in some, like, 2-3 slides back, solving a sequential problem, one part is, as I said, you can use it using this is more of a Lyapunov technique, but other technique is reinforcement learning, or I said MDPs, okay, Markov decision process. Reinforcement learning is more of an AI type of thing, but the math behind is called as the Markov decision process, or like we call it more of abstract or optimal control theory. We have it this term, okay, abstract control and all. So here, if you see RL, you can see, like, as if this is a very simple example how a baby learns, like whether, like, for example, is a fire here. For example, you can think also about there's a cup with a hot milk, and there's one more milk bottle. How he knows? So initially he might not know, so he will touch both of them. So when he touches the hot milk, he will find, okay, it is very hot and must not touch it. But other way around, if he touches the milk bottle, he will be very comfortable with it. So it is learning with the experience, right? That's what I want to say. Same thing is with the RL. Like, you learn, first what you do is you apply your actions, and then depending upon what is the outcome, we call them as a reward. Depending upon the reward, you think about, okay, whether that action was good for me or not. Okay, that's how this RL, like, a bigger picture, works. So the same concept, like the problem which we just explained, like in another research work, we again try to minimize the UI, but here in this case we use the RL concept. So here, if you see, here is a, like, device-to-device communication. Device-to-device communication is a technique in which the 2 devices have a communication without the support of an access point or a base station. Okay, so here we consider like as if there are two devices or they have a point-to-point communication. And however, the packet size are large, so you can't transmit in one time slot. So for transmission of packet, you require multiple time slots. Now, but this, let's assume once again these packets are time critical packets. So if you're transmitting those packets in multiple time slot, and there's also a possibility that a particular packet may get lost or maybe because of the wireless channel, then you have to ensure that if the packet delivery takes more than Zmax delay, then the packet is quite stale or it's obsolete and it's no longer usable. So you want to ensure that the age of the packet, in this case, once again, the packet must be delivered with the minimum age. Okay. So for that, well, since it is a multi-slot transmission, we require Q. Like Qn is the buffer is the like denoted by Qn. We talk about latency. We also talk about age. So this is a very good diagram once again where we talk about how the queue gets updated. So it's a buffer. So let's assume in a particular time slot I transmit xn bits. Okay, beta is the total packet size. At a particular time slot I transmit xn bits. Mu is the problem, like it's a random variable indicating whether packet was successful or not. If it's successful delivered, Qn reduces to xn, like reduces by xn. If it's not successfully delivered, Qn remain as it is. Okay. Then you also have latency, like how long the packet is going to take to get fully delivered, and along with your age. So here, what you can see is like in the diagram, one can think about here. It's a very good picture. Why I'm saying this, because here you can see the difference between latency and age. You can see packet 1 is getting transmitted. Okay, let's assume the packet 1 starts transmitting. It's a big packet, and this is a queue. So as the packets are getting delivered, the queue size gets small and small. But to completely transmit the packet, as if Zmax has happened. Okay, it means like you're not able to send the packet within the stipulated time. Then you are going to start the new transmission. So when you start the new transmission or new packet transmission, the delay, okay, or latency drops because you are talking about new packet. But since age is a concept, because the age is a concept, if packet is not delivered, age starts increasing. Okay, so here the age will still increase, but the delay might have dropped. Okay, but if the packet 2 gets successfully delivered, then the age drops, and then the delay SS goes on. Okay, so this is a very important figure, and I got a lot of things like when I was having the research comments for this paper. This diagram essentially illustrates a very good difference between the latency and the age. So just minimizing the latency is not good enough. So in this case, we wanted to formulate the problem, and as I said, we are formulating as in case of reinforcement learning. Math behind is MDP. So MDP is more about formation of states, a state transition diagram, and there are cost functions. Okay, so here we have state. State indicates what is the current age of the packet, how much packets bits are there in the buffer. Qn indicates that size. Zn indicates for that current transmission of packet what is the latency. Hn indicates the channel conditions. And you always have a state transition. Like if you're moving from this is a state, if you move to next state, what is the probability of moving to the next state? Here we defined, as I said, rewards. So here, for example, if age decreases or increases, that is your reward. Cost is more about how much power it takes to transmit that particular packet as a cost. Okay. So we formulate an optimization problem. As such, we want to minimize the long-term average age of the packets subjected to the power constraint. It's very similar to the problem which we were seeing last time, but much more simplified. So we wanted to formulate this as a MDP. Okay, so for the information in MDP, as I said, you have a state. Now action will be which bits, how many bits you are transmitting. Reward, as I said, will be the power, and will be the age reduction or the power transmission. Policy is on a given state, how many bits you transmit, how much power you use, and all. Those are the policy. The other actions you are taking. So here, if you see in this MDP, okay, this is very like this is more for generic thing where you observe the state. Based upon the observation of state, depending upon the policy, you take action. And the state, you move from one state to another state. Again, you observe it. take action, you move to other state, and that's all it happens. Okay, that's all how the policy is. So you have a state space, all the possible states, action space, what are the possible actions you can take, transition probability, like what is the probability moving from one state to another state, and reward function. Then how to solve this problem? Okay, so like basically how to get the good policy. So there are different types of policy, as I can say. Deterministic policy means what, like for a given state, what must be action. So there's a one-to-one mapping between state and action. Randomized policy means there's a probability distribution over the action space for a given state. Stationary policy, that that probability distribution remains same over the time. Okay. And once again, the objectives can be like as if I want to minimize the reward, or for example, if it's a reward, I want to maximize the reward or minimize the cost over some capital H time frame. It's called finite horizon. It can be infinite horizon if I want to do it for the whole time horizon. Okay. And here you can see gamma. Gamma is also one more factor we introduced. We call it discount factor. So this is something like last class, like last lecture, if you see, the presenter was asking you about the tuning parameters or hyperparameters. This gamma is also like a hyperparameter for us, where we say like if gamma is near to 1, as if I am giving very, like it is more almost like all the rewards in the successive stages are equal weightage. But if the gamma is near to 0, essentially means current reward has a very good weightage, but over the time that weightage goes to 0. So how we solve that? We solve these problems is more about this is a complete theory which exists, and it's a long, it's not a recent one. It's a theory about MDP is very old. And we have got a Bellman equation where we say like, okay, we first define value functions. Value function is the cumulative reward over the time. Q function is like if I take a particular action, then what will the reward? And as such, value function is like which action will maximize my Q value and all. And here, these are all like Bellman equations, a recursive equation which says like what will be the value function if I take this. If take a particular policy, so see, you can see value function is like for a given state. For a given state, if I follow a particular policy, what is the current reward and what will be the some future rewards? Okay. And Bellman operation essentially is an optimality equation where I get a value function for the action which is going to maximize my reward. Optimal policy is something like it's a set of actions which will maximize the reward. Okay, so all these are related. It's a bit math, but it's okay. But then how to solve them? This all are solved using iterative solutions. We have value iteration, Q value iteration, policy iterations. This is more like if you start from initial vector and go on solving the same equation again and again, then you, after some iterations, you stabilize and you reach to a final solution. Okay, so all these value iteration, Q value iteration, policy iteration are almost same. For our problem, so for example, now coming back to our problem where we said like, okay, I want to minimize the age and I want to have a constraint over the power. So this is a constraint optimization problem, and to solve the constraint MDP, what we do is we first, in general, in any optimization problem, if you want to minimize, if you have constraints, you bring the constraints to objective function, and the way you do it by using a Lagrange. So you can see this is a award because of the age plus lambda times Cp minus gamma means how much my power is moving away from the average. Okay, so you can see like this is the like trying to bring the constraint to the objective function. And then relative value iteration is more about this problem is solving average reward problem. Okay, so there's a relative value iteration because I'm trying to iterate my value function with respect to a reference state S0. So that's a relative value iteration. In this work, we went further ahead where we wanted to propose a online solution. This is called as online programming also, where if I don't know the channel quality or if I don't know what probability of successful transmission, still I must be able to go, because since reinforcement learning is about playing with the environment. So even if I don't know how my channel is or what is the probability of success and all, if I start playing with the channel and all, which means if I start taking action with a given power and all, still I must be able to learn how the channel is, right? So that's where this online solution comes up. Okay, and we propose this online solution, and I will not go into the math behind it, but this is like how you can rearrange some of the terms. Okay, what I'm doing is I'm rearranging the terms. We go to something called as post rate allocation state, and we bring up to a solution where we can just get the actions. Okay, you must know what the actions to take and still able to solve the problem. And this was like over the time you have, as I said, you have hyperparameters. So Lagrange variables are there. So Lagrange variables must converge, because if you assume, like Lagrange variable essentially indicates as if I'm able to meet the constraints. Okay, so my power constraints are met. Along with, I must be able to minimize the age of information. So you can see, like, if you have my age of information is like minimized, as well as my transmit power. For example, here I think the constraint was like a 30 milliwatt. I don't know how much it was, 30 microwatt of power. So I must be able, on average, over the time, I'm meeting the 30 microwatt. So this is something like how over the time, like if you like, it's online learning. Initially, you may take a lot different amount of power and all, but over the time, because the sequential decision process, over the time you start getting the required power, as well as your age also decreases, or you achieve the objective function. These are some of the references which we used, and these two works were published, one in IEEE Transaction on Green Communication, and there is CompsNet, and there's another work which we have done subsequently, which is in the review format for the IEEE Transaction. Any questions up to this part? Because after this, I am going to move to something which is a little bit different, which is like how can we use the age of information concept in the massive MIMO communication? Okay, so many of us might have seen massive MIMO communication in some of the research papers, but we are going to use or mix the age of information concept in massive MIMO. Okay, so if we can have the discussion later also. Just to continue. Okay, so we all know massive MIMO is one of the important technologies in the 5th generation and 6th generation communication. But then the point is like, okay, we must also know the wireless channel is not a good, right? If you know the channel, then you can do a lot of things. But if you don't know the channel, then probably if you're transmitting a packet in a very bad channel, then packet is lost. So you have wastage of resources. So in our communication systems, the channel state information, CSI, is a very important parameter. You can also think about MIMO systems. In MIMO systems, when you talk about, if you have a large number of transmit antennas, for example, let's assume we have, and you talk about massive MIMO, we think about hundreds of antennas, right? So from those hundreds of antennas to a user, there will be 100 channels, right? And for each of the channels, you must know the CSI. Now, if I want to know all those CSI, there will be a lot of signal processing needed, right? So sometimes some of the CSI may not be known. If I don't know the CSI, then in that case, whatever the CSI is known, which is the old CSI, then we can introduce the concept of age of CSIT. How old the channel state information is there with me. Okay? So this whole research, which I'm going to talk about, is more about when you're trying to work with the communication system, and if I know the channel, whether the channel is current channel or is a previously known channel. Okay, that's what we are trying to talk. So this is the work which we are doing. Here, as I said, we're going to talk about massive MIMO. In massive MIMO, or any cellular communication, there are two modes. It's called TDD mode and the FDD mode. In TDD mode, it's called time diffusion duplexing. When you say time diffusion duplexing, means I'm going to use the same channel for both uplink and downlink. Okay. However, it's a time division, means in some time frame or some time slot, I'm going to do uplink. Then next consecutive time slot, I'm going to do downlink. Then switch between uplink and downlink over the time. In FDD, we have a frequency division duplexing where we have separate frequency bands for uplink and downlink. Okay. So in this work, essentially we started working with FDD. Okay. But just to inform you all, in 5G communication and recent, mostly TDD are used. Even though FDD is more applicable, the reason is more about channel reciprocity, where since we are using the same channel for uplink and downlink, so you need not require the information, separate channel information for uplink and downlink. So you can, what you can do is like, if you estimate the channel in downlink, you can use the same information for uplink. Okay, so that's where the channel reciprocity works. But in FDD, you must know the CSI for both uplink and downlink channels. So that's the one disadvantage. But there are other advantages also for FDD, because TDD requires a lot of synchronization while you are moving from one base station to another and all. FDD is a little bit less synchronization, so it is a little bit cheaper technology compared to TDD. So this work we talked about FDD, and our objective is like, because every time when your base station in FDD, what happens is like, for example, let's assume you have 100 antennas at the base station and there's one user. So base station, because if he wants to transmit a signal to the user, in MIMO we use beamforming. So for beamforming, you must know the channel. So base station will send the pilot signal. The user will estimate all the 100 channels, and through the feedback channel, which is an uplink channel, now it will get send it to the base station. So there's a lot of overhead, signaling overhead we call it. So our objective was to minimize the signaling overhead by not transmitting the estimated channel to the base station. Okay, and for that, we are going to exploit the temporal correlation. We all know the channel is, some of you asked, what if the channel is like, can we use recurrent neural networks, right? So recurrent neural networks, essentially, I assume there's a temporal correlation. Here also we assume there's a temporal correlation over the channel. Okay, and if there's temporal correlation, then base station, based upon the previous channel information, can predict about the future channel or current channel. However, that prediction will be having certain error. So this work, essentially, what we did was, you can think about, if the channel becomes more old, the beamforming, what we are doing over that information will be not good. Okay, so that will be a detrimental to the downlink data rate. So our objective is always to maximize the downlink data rate. But if you want to maximize the downlink data rate, what would happen is you require always the CSIT. You must know the true CSIT all the time. Essentially means there will be a lot of signaling overhead in the uplink. If there's a lot of signaling overhead in the uplink, then what will happen is you won't have that much time for uplink data. If you don't have time for uplink data, then the uplink data rate will be reduced. So here the problem was, can we maximize the downlink data rate subjected to maintaining the uplink data rate? Okay, so this is the overall view. Here also, we, as I said, we define the staleness of CSIT by age of CSIT. And the solution is almost like what we discussed previously. We talked about relative value filtration. Okay. So here is the system model. You can see, as I said, we have FDD mode, a separate band for uplink and downlink. So in downlink, we are transmitting pilots. Okay, there's a periodic transmission of pilots. In uplink, intermittently or at some time slots only, we are transmitting the channel state information to the base station. So here, how the age, for example, you can still see, like, even if there's a feedback channel, there's always possibility that CSI you're transmitting may be lost because the channel is not good. So here, what you can see is like, this is the pilot broadcast. Now, the down arrow shows the feedback. So, and if there's a crossover, this is an unsuccessful feedback. So if there's an unsuccessful feedback of channel, the age of CSIT increases. The time it becomes successful, for example, it gets successful here, the age drops to the, because you're transmitting this one, So age drops, and then once again, till the time again you're transmitting the CSIT feedback, it will start increasing and then decreasing. So it is like more of a staircase thing. And so as I said, the assumption is the channel is temporally correlated. So here we model the temporal correlation by something called as Jake's model. Okay, where it is a Gauss-Markov model first. The Gauss-Markov model is like the channel at time index n+1 is correlated to the time index at channel time index n by correlation coefficient rho, and WK is some unknown, like, because since there is some innovation, WK is a you can call it aging error. Okay, we call it aging error. So WK and the HK are uncorrelated. Rho K is more of a temporal correlation, so that's why it's called the Jake's model, and it depends upon the Doppler shift FD. Okay, and Doppler shift, you all know, depends upon the velocity or the relative velocity between transmitter and receiver. So here once again we, like, since I said we want to estimate the channel, so we use MMC estimation, I mean mean square estimation for downlink channel. And this equation number 2 tells us like this MMC estimate of a channel which was sent, like for example, if AKN is the age of the channel at current time index n, then what was the estimate of channel when it was transmitted, Hn minus AKN. Okay. And then what we did was like we tried to formulate it as like what is the current channel as a function of the previous transmitted or previously estimated MSC, and along with the channel aging error and the estimation error. Okay, this is more of our equations. And then what we did was with this, we tried to come up with a function of rate. Okay, so rate as a function of age. Okay, so here you can see like we tried here one more thing, we used MRT, maximal ratio transmission, for beamforming. Okay, and with this we came up with the rate expression. This is a rate expression for downlink rate expression as a function of the age of CSI. And also we came up with the formulation like how the downlink, because when you're trying to send the CSIT, you're going to impact the uplink data rate. So how is the, okay, this is on the downlink, but this is also of a uplink. Okay. So here, if you see, this is an optimization problem where we are trying to maximize the long-term downlink data rate. Subjected to uplink data rate must be above constraint. And here in this slide, we tell about, okay, because you're going to reuse some resources for uplink transmission, for the CSIT transmission, your uplink data rate will be changing. Okay. Here, when I was talking about this equation, this is more about when you transmit the pilots, then also you use the certain resources. So how the downlink data rate get impacted by the pilot rate. So here, once again, if you see the problem 6, it is again a sequential decision problem. And we used reinforcement learning again here. And first of all, mathematically, we found it as CMDP. Okay, we defined the state space here. Okay, I will not go in deep. We defined the state space first, and then we formulate, for example, if we create the Lagrange, okay, which is essentially bringing the constraint to the objective, and then solving it using again a relative value iteration. Here we went one more step ahead. Okay, there's something called as the, little bit more about it, but it's called a threshold policy. Like here it says like if when you must send the CSIT feedback. So here what we say, if the age is above the particular threshold, then only you must send the CSIT feedback, else you must not. This is called as threshold policy. This is called. This is a concept where to simplify the solution. It's very like intuitively like, okay, when like if the age of the channel is above, let's say assume 5 units, then only I will send the CSIT. Okay, so that's what we tried to propose, and this is something we show the improvement by simulation here, where we considered 5 users, the distance from the base station, and the required uplink data rate and all. Okay, and we showed like, okay, if you just are transmitting for example, if we just focus on improving the downlink data rate. So if you see the figure, the dotted line shows the improvement in downlink data rate by continuously transmitting the CSIT. If you do that, then the uplink data rate, if you see, it is drastically reducing with the number of base stations. However, the proposed solution, what we are showing was like the uplink data keeps on increasing, whereas you are still able to meet the uplink constraint. So your downlink data rate is increasing, but you are meeting the black curve shows you're still meeting the uplink data rate requirements. Okay, so this was something like how you can optimize between the two requirements. This figure shows how the temporal correlation, okay. For example, if you see temporal correlation is like how the channel is correlated over time. So if I say the value is in the range from 0 to 1, so if near to 1, the channel is highly correlated. Channel is highly correlated means I must be able to better predict the channel. If I'm able to better predict the channel means no need to transmit the CSIT. So then the downlink data rate will improve. So you can see like the row when it's near to 9, you have very good downlink rate. Okay. However, as the row decreases, downlink data rate decreases. Okay, because you are not able to predict the channel well. This one shows about the pilot periodicity because base station is also transmitting the pilot after a few frames. So if the periodicity decreases, right? If, for example, if you see if you're not transmitting the pilot frequently, then obviously the channel state information will be stale and the downlink data rate is going to reduce. Okay, that's the quantitative result. So we did this, and right now we have basically extended this work where we are trying to optimize both the feedback channel as well as how the pilots must be transmitted over time and through when we have more users and all. And right now the work is again reviewing one of the sessions. So this is a little bit conclusion. Like this was for at least for the massive MIMO where you have a lot of overhead for channel state information. You can always characterize the delay, for example, age of channel state information by a metric called age of CSIT. And with this introduction of metric, you are able to take a balance, or you are able to manage both uplink and downlink data rate. Okay. These are some of the references, and the work which I just presented was published last year in ANTS, and some work is still in progress. Okay. With this, I will stop, and I will now be answering your questions if you have. Okay, any questions if you have? Even though this lecture was more of a theoretical one, but if you have any basic questions regarding what is the age, because this is something new for many of you. So if you have any questions regarding the age concept and all, you can always ask.
So participants.
Also, this is quite late now. It is almost near to 9. So.
Yeah. So you can unmute and ask the questions.
I think probably many of the participants might have gone for dinner.
No, there are around 217 people.
Okay, 217 people, yes, including us.
Sir, one question is there.
Yeah.
I think if you can read in dynamic environment like UAE, relay-based communication, what additional aspects to be considered for CSI between drones and users?
So where can I read the question directly? Okay, I was trying to read it.
Chat. There is
Okay,
a chat.
is there, not Q&A, chat. Yes. Okay, so in dynamic environment like UAVs, relay-based communication, what additional aspect to be considered for CSI between drones and the users? Okay, so remember in UAVs, for example, see, channel state information is required. Right? You must understand, even if you are talking about UAV, even though there is a direct link as far as, because in UAV normally we don't have reflections. Okay, it's a direct link. So in those cases, once again, what I can think about is if you want to, for example, here, what is the backhaul? In UAV, again, if you think about, if you are, is a relay, so there's a massive MIMO base station, then you have a connection to the UAV, and from UAV, you're trying to give coverage to the users, right? Maybe. So in that case also, for example, if you think about it, there are also a lot of signaling overhead will be there. So if the signaling overhead is there and that is impacting the performance, okay, of communication, or because UAV you are trying to give coverage to the users, if it's impacting that performance, you can think about how to minimize the signaling overhead. Okay, so this is a very important research topic which is going on in reducing the signaling overhead when we have large number of antennas. So there also in IRS also you can think about there are large of atom antennas, right? So in IRS also there's a problem. We are all talking about IRS at the moment, but nobody is talking about what is the problem with the channels, right? Because you have to like if you've seen lots of coding or lots of papers, they assume sometimes you know the channels. Right? So, but knowing the channel is not that easy. So there also you can try to use some of these techniques to minimize the overhead requirements. Next question is, which channel model will be more suitable for beyond 5G and 6G other than Jake's channel model? Okay, see the Jake's channel model is quite simple. Remember this, like when we start any research work, we don't start with a very complicated model. But you can go for much more complicated, like if you have, when we're talking about higher correlations, right? When we have larger temporal correlation, when we also like in one of our research work, we also talk about spatial correlation, both spatial temporal correlation over the channels we're talking about. In those cases, there are different models which are there, which are coming up, but I will suggest in such cases, we are using a machine learning thing for some of these spatio-temporal correlation. But one of you or like whoever is interested, you can also use graph neural networks. GNNs are there, where you can use both spatio-temporal signals. Okay, so Jake's model is prominently used, but others are also there. What about the best method for communication considering 6G channel model in drone technology? What is the best method for communication considering 6G channel model in drone technology? Okay, I believe now I'm getting about this. When you talk about 6G channel, right? So you're talking about something, the channel in 21, we call it FR2 band, right? 21 gigahertz to 52 gigahertz. So it's a very like higher frequency band. So in those bands, we have to first see what will be the what do you call it? How the temporal correlation or the spatial correlation there. We call it like correlation. What are the terms? I forgot. Because in those high frequency bands, normally we are transmitting, like if you are using large antenna array, you're transmitting a very narrow bandwidth, a narrow beam you are transmitting, right? In those cases, these are short distance communication, even though, but channel models, like when you're talking about 6G channel models in drone technology,
they're sparse, right?
Yeah, they are sparse, but exactly for the drone technology, I'm not sure. Now these are in FR2 band only. I think they are talking about, but because for 6G FR2 is mostly nowadays is coming up.
Actually, as per the that is what they are saying is FR2. You are saying 7 to 8 gigahertz.
No, sir. 7 to 8 gigahertz. FR2 will be about 21 gigahertz, sir.
Yeah. Now they have freezed that for Indian scenario FR3. I think it is above 6 to that is 7 to 8 gigahertz.
Okay. So that but that is also very high frequency
actually ମୁଁ online evening ବେলা କରିଥିଲି ତ କଲେଜରେ ପଚାରନ୍ତି ନା ବେଳେ ବେଳେ କି କଣ
Okay, sir. There was some external.
For drone, I am not sure exactly because drone, I think because normally drones are used in the feedback. Like you have drones are normally nowadays are used for unmanned aerial base station, right? UAVs, and they are trying to provide the coverage. So one part is serving the users. Other is a backhaul between the drone to the base station or like remote base station or using that. So I think because drone, what type of channel? I'm not sure exactly. I have to check.
Actually,
for 6G, I'm not sure.
What I have heard or seen, what some of our colleagues are doing is they are using a 5-point model, channel model for drone technology because it's a very dynamic channel.
Mm-hmm. Now you can use Poisson point process for that, but I'm not exactly sure about it. Okay, I have to check. Any further questions?
Yeah, I think no more questions. I wanted to ask. Actually, sir, we use CSI that is deep learning techniques for CSI feedback.
Autoencoders and all. Yes.
Yeah. So the way you said it is like it is also very interesting. Like you reduce the overhead by considering the age of the channel.
Yes.
Is that?
Then you are not transmitting it. In autoencoders, sir, you essentially what you're saying is like the channel is correlated.
Yeah.
Okay, so you are trying to compress by bringing from that larger domain to some latent or smaller dimensions you're bringing it up. Right. So autoencoder is a good technique. So in one of our work, we will be like mixing the autoencoder along with the age.
Okay.
It will further reduce the amount of signaling overhead.
Yeah, this is a very good thing where first we reduce the aged channel and then then it would reduce overall.
Yeah, that will reduce completely, right? Like,
yeah.
One is like you can think about when you're using autoencoder, it's more about using like it's a spatial correlation between the channel. You're trying to exploit that. Other part is we are trying to exploit the temporal correlation. So both of them you can do it. And in one of our research work, we are also thinking about correlation between the users. Like if the two users are nearby, the channel will be correlated. So can we exploit such information also to minimize the overhead? So there's lots of scope, and we can think about it.
Yeah, it's a very good problem.
Yes.
I think that they are asking, share the PPT related to this session.
Yeah, I will share that with you, sir. And then you can forward it.
Okay. So I think we can wind up. I think it's 9 o'clock.
Yeah.
Thank you, sir. Very interesting and very exciting topic. and also we could get some of the new problem statements from this particular topic.
Yeah,
I
thank
believe
you.
all the participants also could get the sight of the that is topic, which was very novel and very interesting topic. Thank you, sir. Thank you very much for
Thanks,
considering
Lord.
our
It was a little
invitation.
bit like it is a little bit because since a new topic, it is sometimes you need to hear it patiently because many a times we are not able to get the things. But you can search some of the papers and you will feel like okay, because many a times we are working with just throughput and delay and we don't find a novelty in the work. But if you see these concepts, and I think we can apply in very different, like as I started using this concept for the channel, but you can apply the age concept in different other network parameters also. So
Yes, yes.
feel free and you can think about it. It's a lot of new venues will come. Yeah. Thank you.
Thank you, sir. Thank you and good night.
Yeah. Good night to all. Thank you, sir.